Good afternoon, everyone. I've the last presentation slot of the day before the panel discussion, and will complete a quartet of CHERISH presentations, through which we hope we have given you an overview of the totality and cross-disciplinary nature of the CHERISH team and our project. Anthony started the day with an overview of the project, while Sarah looked at the project's paleo-environmental and dating work in reconstructing past environments and weather history. Kieran took us to sea to showcase our work in the maritime zone. And now I'm finishing by taking us back to dry land, though with some wet feet in the intertidal zone, looking at CHERISH work on the coast edge. There are three main aims of our work in this area. The first is to target data and knowledge gaps to enhance the historic environment record, thereby improving the data and evidence base to assist future monitoring, planning, and research. This image is an example of Covline from the Royal Commission, one of the historic environment records available in Wales. In both Wales and Ireland, all CHERISH data will be made widely and freely available through the historic environment records and archive resources. The second aim is establishing new, metrically accurate baseline data sets of heritage sites around the coast of Wales and Ireland. This will assist with future monitoring, improve our understanding of the threats, and assist with the management of sites. Our final aim involves taking action, undertaking archaeological investigation at threatened sites to improve our knowledge and understanding of them before valuable information is lost. The historic environment is a precious and finite resource. It's therefore crucial we do all we can for it. All of the three aims I've just outlined are important in climate change adaptation, the process of adjustment to actual climate change and its effects. CHERISH provides information that will help achieve better outcomes through planning and anticipating adaptation. This may be low intervention with some simple maintenance and repair to improve resilience, but equally it could be high intervention, managed loss with preemptive preservation by record, as showcased here. What I'm going to do now is showcase some examples of CHERISH work on the coast edge and in the intertidal zone, which encompass the aims just outlined, but draw on the range and scale of our work from the national level to landscape and individual site level, and from metre down to millimetre data resolution. This work obviously encompasses our toolkit approach, drawing on and integrating technologies and data available to us. In the case of the coast edge, this encompasses those aerial and land-based techniques circled in red. I'm going to draw on three examples of our work in targeting data and knowledge gaps to improve our understanding of the historic environment. The first is light aircraft aerial reconnaissance, providing national coverage and offering a quick and reactive response to events where large areas of ground need to be covered. For example, post-storm monitoring, low tide monitoring, and as shown in this image, reconnaissance during drought events, looking for new archaeology revealed as crop and parch marks. This is an image taken during the drought of 2018 and shows a newly identified prehistoric defended enclosure near the coast edge at Marloes in Pembrokeshire. This was just one of many new sites discovered that summer. It is an example of one of the few positive effects of climate change on the historic environment. In Wales, our main focus on targeting data and knowledge gaps has been on islands, as we are fortunate that in the 1990s, the Welsh Archaeological Trusts undertook coastal zone assessments of the main coastline of Wales, and thus our historic environment records in that area are very good. Given their size, in some cases remoteness, and the fact that many are highly protected landscapes for wildlife, our approach to recording these landscapes needed to be as non-invasive as possible. Therefore, LiDAR, or aerial laser scanning, was the ideal solution. During low tide in 2017, LiDAR was captured for us by Blue Sky International on 6 Welsh islands: Skerries, Puffin, Bardsey, Todwalls, Ramsey, and Grousehole. The 25 centimetre LiDAR data provides the first highly accurate 3D geomatic data set for these islands and adds to the open government LiDAR data for the coastlines of Wales and Ireland, which range in resolution from 0.5 to 2 metres. The data gathered has been analysed using the Real Visualisation Toolbox. This image shows Ramsey Island digitally illuminated through processing high data in a variety of ways, enabling us to see more than we ever would on the ground. Using this data, combined with other resources such as historic and current aerial photography, historic maps, and documentary research, and followed up with ground reconnaissance, we've been able to create new archaeological maps of the islands, enhancing our understanding of these historic landscapes and identifying archaeological features not previously identified. In Ireland, where there are no previous coastal zone assessments, the CHERISH team has started the process, undertaking coastal zone assessments through the analysis of project UAV data combined with walkover survey. 2 coastal areas along Ireland's east coast and 4 islands have been the subject to coastal zone assessment. One outcome of coastal zone assessments across the UK has been initiatives such as Scotland's Coastal Heritage at Risk project and Citizen in England, which work with individuals and communities to provide additional data and longer-term monitoring of the archaeology in the coastal zone. These use an app which allows volunteers to gather and submit information, and a similar app is planned for development this year in CHERISH. Now moving back to look at our baseline monitoring. Across the CHERISH study area, we have some 40 heritage sites, those in Ireland are shown on this image, which we term our baseline monitoring sites. These include different environments, coast edge, intertidal and maritime, and a variety of monument types, shipwrecks, peat deposits, promontory forts, and buildings. At our baseline monitoring sites, we have gathered at least one, and in some cases more, epochs of data, using and integrating data gathered through UAVs, laser scanners, and GPS to provide data sets with accuracy of around 5 centimetres and under. Such resolutions ensure that change can be accurately monitored. Our monitoring of sites is both scheduled and reactive, and we have established relationships with owners and locals who have become our eyes on the ground and who notify us of any changes. Repeat survey and observation helps us to understand what the exact pressures are for a heritage site. For example, is erosion the result of cliff collapse following extreme events such as storms? Or is it due to increased ground moisture and precipitation, or indeed cumulative impacts? Once we identify these pressures, some may be addressed through management, for example, maintenance or repair. At others, the data will assist in programming more active intervention. We hope that a legacy of the project will be that many of these sites will continue to be monitored, building up data and statistics that will help in climate adaptation and management going forward. To assist with this, and to make the task easier, we are fixing permanent survey markers with georeference coordinates at a number of sites. This is an example of our monitoring work at Dunbeg Promontory Fort in County Kerry, a site occupied during the 6th to 11th centuries, and for which part of the fort's defences and main dwelling survives. Due to its exposed location, Dunbeg has suffered many episodes of collapse, largely the result of storm activity. Large-scale change has occurred during the duration of our project and is being recorded by CHERISH. Using a UAV, we surveyed the site in 2017 and 2018. Each survey was georeferenced using ground control points surveyed in GPS and processed using structure from motion software at a soft metashape. Comparative analysis of the resulting orthophotos and 3D models indicates some 3,000 meters cubed of the cliff face and monument was lost following Storm Ophelia in October 2017 and Eleanor in January 2018. In the dynamic intertidal zone, we have been monitoring a series of shipwrecks. These are visited during low tides, but also following storm events or notification of significant change. This helps build up a picture of exposure against weather patterns and conditions such as wind direction, which in the long run has the potential of helping to target fieldwork. This example shows a relatively stable shipwreck, while stable in terms of location, but with changing levels of exposure, located near Abersoch on the Llŷn Peninsula in North Wales. Contrast that with another of our monitoring sites over on the west coast of Ireland in Kerry. In January 1904, the wooden schooner Sunbeam was driven ashore in a storm and wrecked at Ross Bay. Since the time of wrecking, the Sunbeam has formed part of the seascape of Ross Bay Strand, sitting in the exposed Atlantic intertidal zone. This map shows the movement of the shipwreck between 2013 and 2018. The most southerly black star marks its location in 2013. The star located approximately 100 meters to the north shows her location after Storm Christine in January 2014. The black star at the northern end of the Ross Bay Spit shows her location when rediscovered by the CHERISH project in October 2018. It had moved some 3 kilometers along the strand, a result of the severe winter storms during the winter of 2017-18. Data gathered during our monitoring of sites also enables us to produce a range of products for more general public consumption, helping us to raise awareness of the impacts of climate change. Video, as seen here for Carvai Promontory Fort in Pembrokeshire, provides highly visual and engaging content. The resulting digital elevation models produced from our surveys can also be printed, as seen here with Dinas Dintley Coastal Fort in North Wales. This is a great showcase and has been used at face-to-face events such as talks, walks and school visits, and will be a feature of future exhibitions. For the virtual audience, the data has also been used to create a Sketchfab model. And this is something we've done at a number of our study sites, all of which can be accessed via the CHERISH website. This sample is again Dinas Dintley. Once loaded, you can pan around and zoom in and out of the model. Added information points or hotspots also provide the user with a virtual guided tour, exploring a range of themes covering the hill fort's history and archaeology, its complex geology, and the erosion processes affecting it. It's also possible to inspect the model, remove the render to look at the standard surface model, and also view the underlying wireframe. So far, I've outlined the data gathering side of CHERISH work on the coast, largely for the purpose of impact monitoring. But for sites at threat, it's essential that we increase our understanding of them before loss. At a number of CHERISH sites, we've therefore undertaken a variety of investigations, non-invasive and invasive. Ferreters Castle and Promontory Fort on the Ballyferreter Headland, Dingle Peninsula in County Kerry occupies a long, narrow promontory extending over 500 metres from northeast to southwest. This promontory has been utilised and adapted in the construction of the Promontory Fort with a series of banks and ditches forming an outer and inner set of defences. A 15th or 16th century tower house, Ferreters Castle, was later constructed on the inner bank of the defences. In addition to the UAV survey and laser scanning of the promontory undertaken by the CHERISH team from the Discovery programme, geophysical survey has also been undertaken to reveal more information about subsurface archaeology and visible archaeological features such as hut sites within the boundaries of the fort. A programme of excavation is now scheduled for later this month. As a final example of integrating all our methodologies, I'll now turn to the final case study, Dinas Dintley in Gwynedd, North Wales. Here, a late prehistoric coastal hill fort is constructed on a hill of glacial moraine, overlooking the surrounding low-lying coastal plain. Using maps and 25 centimetre LiDAR data, we've analysed erosion at the site since 1900. In this time, upwards of 50 metres of the western side of the monument has been lost, and based on these rates of erosion, not even taking into account climate change predictions, we estimate that the whole monument will be lost over the next 2 to 5 centuries. Erosion here is happening incrementally, but also through major localised collapses, as seen in the 2 UAV images, which show the before and after of a substantial collapse in the cliff face at the end of January 2019. This clearly exposed a section of the hill fort's inner ditch. During the lifespan of CHERISH, we've integrated technologies for our monitoring and have used 3 techniques to gather data. For the actively eroding cliff face, an area just over 300 metres, we've undertaken laser scanning to provide a data set at the highest resolution to a mean error of 4 millimetres. For the whole monument, including an area around it and the intertidal zone, we've undertaken UAV survey using a DJI Phantom 4 Advanced and have gathered 4 sets of monitoring data in 2018, 19, 20 and 21. Compared to laser scanning, this is a relatively rapid process in the field with overlapping images, mainly vertical with some obliques, gathered over a 3 to 4 hour period. Roughly 1,500 images taken at an altitude of around 70 metres and producing a digital elevation model with a resolution of 3.5 centimetres. Our UAV monitoring survey undertaken in September 2020 coincided with the spring tides. Here we linked to a CHERISH partner, the Geological Survey of Ireland, who undertook marine survey at high tide. The right-hand image shows the raw multi-beam data gathered as viewed on board the RV Keary. On land, the CHERISH team from the Royal Commission undertook the UAV survey at low tide. Once processed, we're hoping that this will provide the overlap needed to close the white ribbon zone and thus produce a seamless offshore-onshore model of the study area. We've also undertaken a variety of investigations, non-invasive and invasive, both within the hill fort and the surrounding landscape, as shown in these images. This has been undertaken by the CHERISH team, but also through work we have commissioned, which thus far totals nearly €90,000. An example of non-invasive work has included 3 different forms of geophysical survey. Initially, magnetometry to identify remains within the hill fort and in a field surrounding it. Based on these results, we then commissioned targeted resistivity in the hope of gaining more information concerning a mound in the interior of the hill fort, and ground-penetrating radar to help more clearly understand the depths of deposits and archaeology. Main highlights from these surveys include a busy hill fort interior with evidence of roundhouses, roads and divisions, a newly identified ditch which may indicate a northern annex to the hill fort, the course of a sinuous approach from the south leading through the southeastern entrance, and archaeology to the south of the hill fort, including fill systems and medieval and post-medieval settlement. Invasive work has included 2 excavations, the first by the CHERISH team targeting exposed archaeology in the cliff face, particularly that of the inner ditch section shown earlier. A good head for heights and a safety expert is essential for this type of work, though it is costly and difficult, and the archaeological survival varied. Thus, for known archaeological sites, a much better methodology is a targeted programme of excavation rather than a last resort excavation at the cliff face. Having said that, recording the exposure of the inner ditch in the cliff face was a much quicker method than that of a trench excavation. Once cleaned, we used the USV and survey control to produce a photogrammetric image of the complex section, which was subsequently drawn up in AutoCAD. Our second excavation was a community one, run for us by the Gwynedd Archaeological Trust. Over 2 weeks, a series of 8 trenches were excavated both within the hill fort and in the field to the south, all targeting anomalies from the geophysical survey. Over 50 volunteers took part, the majority from the local area, and an open day attracted over 400 visitors. Here and at other sites, we've worked hard to involve and engage the local community who have provided us with a wealth of information, a great interest and willingness to help. At Dinas Dintley, the community excavation was a great success with some exciting discoveries. Outside the hill fort, we uncovered evidence of Neolithic activity, medieval and post-medieval settlement, and within the hill fort uncovered an exceptionally well-preserved and large stone roundhouse, 13 metres in diameter, along with a small Iron Age hammerhead, the first of its kind found in Wales. Such a wealth of archaeology showcases why it is so important to undertake research and investigation at threatened sites. Further excavation is now planned, working in partnership with the National Trust, Cadw, and the Gwynedd Archaeological Trust. And finally, both excavations also revealed a story of sand, many tons of it filling the inner ditch of the hill fort and also covering the archaeology in the trenches, all evidence of past storminess. Here, the CHERISH team from Aberystwyth University have recovered samples for luminescence dating, which provide us with a date for when the sand was deposited. I'm going to draw things to a close there, other than to say that over the next few years, our work will continue at all our study sites, with the results drawn together for publication and information provided to owners to assist with management and future monitoring. We'll also be creating new interpretive products produced, such as reconstruction drawings and animations, all linking back to the overarching aim of CHERISH to raise awareness and understanding of the past, present, and near future impacts of climate change on the rich cultural heritage of our sea and coast. Diolch.